Precalculus Lesson 16 continues with an introduction to logarithmic functions. This is from section 4.1 in the College Algebra textbook. We start with a definition. For y greater than 0 and b a positive number other than 1, log to the base b of y, also referred to as a logarithm with base b of y, is the power of b that gives y. What this means is, for example, log to the base 3 of 81 is 4, since 4 is the power of 3 that gives us 81, or 3 raised to the 4th equals 81. Log to the base 1/4 of 64 is negative 3, since 1/4 raised to the power of negative 3 is equal to 4 raised to the power of 3, which is equal to 64. Now for the equivalency between logarithmic and exponential equations. Log to the base b of y equals x if and only if b raised to the power of x equals y. We think of this as the same equation, simply written in different forms, the first being the logarithmic form, the second being the exponential form. To transform an equation from one form to the other, we note where the exponent occurs in each of these forms and also where the base is. Another thing to note is that a log is an exponent, and that will help with converting from one form to the other. Let's convert the equation log to the base 5 of 125 equals 3 from its current logarithmic form into exponential form. I first look for the base, which I can easily grab just reading left to right, log to the base 5. So the base here is 5. I'll write the number 5 here. And then a log is an exponent. So our exponent that goes on that 5 is 3. The number that's left over here is 125. So we have 5 raised to the third equals 125. Now to convert the exponential form of 3 raised to the power of negative 4 equals 1 over 81 into logarithmic form, I start by writing the word log. Then I look for the base, which I can see would be 3 here since we have 3 raised to the exponent of negative 4. So log to the base 3 of, I usually just leave a space, then put an equal sign to the right of some empty space. On the right of the equal sign, I'm going to write the exponent, which in this case is negative 4, and then go back and look, well, what number did I not use yet? And that would be 1 over 81, which we will put here as what you can think of as the argument of our log. So I have log to the base 3 of 1 over 81 equals negative 4. Now let's solve some logarithmic equations by first converting to exponential form. Log to the base 4 of x equals negative 3 to begin with. And so I look for the base here, which would be 4. So I'm going to write this equation in exponential form with a base 4. Note that a log is an exponent, so our exponent here would be negative 3. 4 raised to the negative 3 equals x. 4 raised to the negative 3 is the same as 1 over 4 cubed. And so I have x equals 1 over 4 cubed, or 1 over 64, and we have a solution. For log to the base 1/2 of 3x minus 5 equals negative 4, the base is 1/2. 1/2, converting to exponential form, would be raised to the power of negative 4. So 1/2 raised to the power of negative 4 is going to equal 3x minus 5. 1/2 raised to the power of negative 4 is the same as 2 raised to the 4th. And 2 raised to the 4th is 16. So 16 equals 3x minus 5. Adding 5 to each side gives 21 equals 3x, and then dividing through by 3, we get x equals 7 as a solution here. Okay, a definition of a logarithmic function with base b is that a logarithmic function with base b is f of x equals log to the base b of x, where b is a positive number not equal to 1 and x is greater than 0. As an example, we have f of x equals log to the base 3 of x, or g of x equals log to the base 1/4 of x. And just to note here, these are what I would refer to as a basic logarithmic function. Let's move on and graph the basic logarithmic function. F of x equals log to the base 2 of x. The first thing I do here is I think of this as y equals log to the base 2 of x, and I then change from logarithmic form into exponential form so that I will be graphing x equals 2 raised to the y. So the first thing I'm noting here is that x equals 2 to the y has x as a function of y. So while we usually start by plugging in x values to figure out what y is for points on our graph, here we're going to start with y values and figure out what the corresponding x values would be. So if y equals -1, x would be 2 raised to the power of -1, or 1/2. If y equals 0, x would be 2 raised to the power of 0, which is 1. And if y equals 1, x would be 2 raised to the power of 1, or 2. Now we have 3 points to plot on our graph: 1/2, -1, 1, 0, and 2, 1. We connect these 3 points with a nice smooth logarithmic curve and note some characteristics of the curve. First of all, the domain here, while it looks like our graph is almost touching the y-axis, it gets so close. It never in reality does touch the y-axis, and so the domain would be all real x values greater than 0, 0 to infinity. The range includes all y values here, so is -infinity to infinity. We have the asymptote, which is the y-axis. We would refer to that as the line x equals 0. And on the graph of any basic logarithmic function is the point 1, 0. Okay, let's look a little more at this. The graph of this function, f of x equals log to the base 2 of x. Along with the graph of f of x, I'm going to put the graph of g of x equals 2 raised to the power of x, and let's look at some common characteristics between these two functions. First, you will note that each of these is a one-to-one function, which should tell us, well, these functions might have an inverse. And in fact, the two functions are inverses of each other. And we can tell that graphically by looking at the line y equals x and noting that the graphs of the two functions are symmetric about the line y equals x. In fact, on the graph of the logarithmic function, we have the point 1, 0 and the point 2, 1, while on the graph of the exponential function, we have the point 0, 1 and we have the point 1, 2. So something else to note is that the domain of f of x is the same as the range of g of x, and the range of f of x is the same as the domain of g of x. Let's go on to graph g of x equals log to the base 2 of x plus 3, and here I will start with the graph of y equals log to the base 2 of x. And all I need to do here is shift this graph to the left by 3 units to give us a graph of g of x. Note that in addition to shifting the graph to the left by 3 units, the vertical asymptote of x equals 0 also shifts to the left by 3 units. So we now have a vertical asymptote, x equals -3. The domain changes a little bit as we shift to the left by 3 units. We now have the domain of -3 to infinity, not including -3. The range stays the same, all y values, or -infinity to infinity. Let's look, before closing out this lesson, at bounds on logarithmic expressions. I want to determine 2 integers that bound this logarithmic expression, log to the base 2 of 35. Well, we've been graphing f of x equals log to the base 2 of x. And something we note here is that the graph increases going from left to right. And so from that, I can get that log to the base 2 of 35 is bigger than log to the base 2 of 32. and is log to the base 2 of 35 is smaller than log to the base 2 of 64. Why did I pick these two? Why did I pick log to the base 2 of 32 and log to the base 2 of 64? Well, log to the base 2 of 32 is the power of 2 that gives 32, or 5. Log to the base 2 of 64 is the power of 2 that gives 64, or 6. So we get integers for both of these logs, and right in the middle there would be log to the base 2 of 35. So I have bounded log to the base 2 of 35 by the integers 5 and 6. And I also note if I actually plugged log to the base 2 of 35 into a calculator, I would find that it's approximately equal to 5.129. All right, so it's closer to 5 than 6, but it is between 5 and 6, as we've shown by bounding it by those two integers. Try on your own number 2. Solve the logarithmic equation log to the base 7 of 4x plus 3 equals 2.